In today's lesson, section 7.1, we're again going to look at the area between two curves, but now we're going to take it with respect to the y-axis. So what is that going to look like? So now we're going to have a graph. Maybe we'll have our graph looking like a sideways parabola, and then a linear function coming through it. Maybe something like that. Notice now we've got a region created between those two graphs. In order to find the area of that, we could find this region and this region, or find these points of intersection, just like we did the other day. However, sometimes it's easier to find the points on the y-axis. So maybe this is our A and our B value, and then we can find the area of the right curve minus the area of the left curve that's created. So now we're looking at higher x values versus lower x values, whereas before we were looking for higher y values versus lower y values. So let's go ahead and look at example 1, and maybe it'll make a little more sense to us. If I give you x equals 4 minus y squared and x equals y minus 4, what does those graphs look like? Hopefully, many of us know what this is going to look like. 4 minus y squared, we could factor that to y minus 2, or 2 minus y and 2 plus y. So we would know that y equals 2 and negative 2. So we know that we go through the y-axis at 2 and negative 2. It's a negative y squared. So we know that we're going to be opening toward the negatives. And we know that we go through the x value of 4. So we should see a graph, hopefully in our mind, that looks something like this. Now if I look at x equals y plus 2, or y minus 2, that one would be pretty easy to go ahead and solve for y. Y equals x plus 2. And if I graph that, then I've got my 2 there. I have a slope of positive 1. And it's going to look something like that. So my area is in here. Now some of you might say, hey, why can't I just go ahead and solve for y and get those equations into y equals form and integrate it that way? And you can. The problem is, if I take x equals 4 minus y squared and solve for y, well, I'm going to subtract 4. So I get x minus 4 equals a negative y squared. Multiply my negative through. I get negative x plus 4 equals y squared. And I'm going to take the square root of both sides. So now I have plus or minus the square root of negative x plus 4 equals y. Now we're going to be integrating a radical, which substitution might help us. Otherwise, we'd have to come up with another means. Also, if we're looking with respect to the x-axis here, notice from this point over to here, the x equals 0 line, our top curve is this linear function. Our bottom curve is the negative radical. Whereas over here, our top curve is the positive of the radical minus the negative of the radical. So that gets to be very cumbersome, because then we have two integrations that we got to work with. Doing it in forms of the y-axis, I can find these 2 points of intersections, and I'm looking at the y values now. So again, we can do a substitution. We know that y, or 4 minus y squared equals y minus 2. Solving, or setting this equal to 0, we have y squared by moving the negative y squared over, plus y. Then I can subtract my 4 and we get 6. So we get y squared plus y minus 6. If I factor that, I get y plus 3 and y minus 2. Setting each of those equal to 0, I know that y is going to equal negative 3 and 2. So again, I know that this value is negative 3, this value up here is 2. So I'm going to integrate down here from negative 3 to 2 of my top curve, but now I'm looking at the right curve. The right curve in this case is that quadratic 4 minus y squared minus the left curve, which is y minus 2. And my variable of integration becomes y. So I've got a dy at the end. I can integrate this, negative 3 to 2, 4 minus y squared minus y plus 2 dy. Cleaning that up, I'm going from negative 3 to 2, negative y squared minus y plus 6 dy. I can integrate that. So we'll come over here, negative 1/3 y to the third minus 1/2 y squared plus 6y from negative 3 to 2. Plug in your 2, plug in your negative 3, and get your value. So what do we have? Negative 8/3 minus 2 plus 12 minus, plug in your negative 3, we get negative 27 divided by negative 3 gives us 9 minus 9/2 minus 18. And that'll give us our value. You can plug it into your calculator just the same as I can. If we have a calculator, again, we can integrate at any point in time in here. We could calculate this, come over here to our y's, and our life becomes fairly easy. It would be down in here where our calculator would really be easiest to use. We can change these variables to x's in our calculator. So we could integrate the negative x squared minus x plus 6 dx from negative 3 to 2 would give us the same answer. In example 2, just another problem. Allow us to work a little bit more with it. Again, I can go ahead and graph this. Y times y minus, or 4 minus y. If I set those equal to 0, to find my zeros of this, I know that y equals 0 and y equals 4. So I got my 0 here and I've got my 4 up here. I also know that it's going to open toward the negatives because I have a negative y squared. If I were to multiply this out, I get 4y minus y squared. So I know I'm going to come up like this and then come out something of that form. If I graph x equals negative y, well, I can also say that that is y equals a negative x, which is more familiar to me. So I start here at 0. I'm going down 1 and over 1, so my equation, my graph, is going to look something like this. Again, I have to find these points of intersection, but I'm looking for the y values. So again, we can set those two equations equal to each other, and I've already multiplied it out, so I might as well use it. So 4y minus y squared equals a negative y. Setting equal to 0, I get negative y squared plus 5y. Solving that, we can go and factor out a negative y if you want. So we get y minus 5 equal to 0, so y equals 0 and 5. So I'm integrating from 0 to 5. There's my 0, there's my 5. My top curve, now in this case, my right curve, is going to be my quadratic, 4y minus y squared, minus my left curve, which is going to be a negative y dy. Again, integrating from 0 to 5, negative y squared plus 5y dy. I can integrate negative y to the third plus 5y squared over 2 from 0 to 5. Plug in our 5, we get negative 125 thirds plus 125 halves minus, plugging in my 0, I get 0. So you get negative 125 thirds plus 125 halves. We can find, again, another common denominator. So we're going to multiply that. We get negative 150 plus, what do we get, 375 over 6, which gives us 125 sixths as our answer. Again, we could throw that in a calculator if you want. Go to math, 9. We're integrating from 0 to 5. My function, which is negative x squared plus 5x dx. We hit enter, and we get our math, our fraction, enter, gives us our 125 over 6. So again, remember, this variable is arbitrary at this point in time. We can let it be x's, we can let it be y's, we can let it be a's if we wish. I have one more example. In here, we have y squared plus 3, y equals 0, and we're going from 0 to 2. So again, what does that look like? Well, in this case, y squared plus 3, our x-intercept is 3, and this parabola is going to open to the right. I know that because I have a positive y squared. Here, g of y equals 0, so I'm going to go down through the axes, the x equals 0 axis, and I'm going from 0 to 2. So now here's my 0, and here's 2. So to integrate, I'm going from 0 to 2. My top curve is y squared plus 3. My bottom curve, in this case, is 0. In this case, we don't have to put the 0, but I'm going to just have it as a placeholder, dy. Clean that up. I have the integration from 0 to 2 of y squared plus 3 dy. Now I can go ahead and integrate. We get y to the third over 3 plus 3y from 0 to 2. Plug in the 2. We have 8/3 plus 6. Plug in the 0. We get 0 again. So 8/3 plus 6. Well, 6 is 18/3. So 8 plus 18 gives us 26/3. And that allows us to find the area with respect to the y-axis.